Hello everyone, and welcome to today's webinar, Best Practices for Amazon Web Services Redshift Optimizing Performance. I'm Greg Kerala, Business Development Manager for Redshift at Amazon Web Services. Today's speakers are Sanjay Kocha, a solution architect with extensive experience in Redshift, as well as Eric Fiera, one of our principal database engineers, who will be helping us with questions and answers. Just to let you know, today's webinar is meant for advanced users that are familiar with Redshift. If you're new to the Redshift platform, please refer back to our June webinar series, Getting Started with Amazon Redshift. Today's best practices will be the first in a three-part series. Today will be based on optimizing performance. Tomorrow, at the same time, we'll be doing a webinar that focuses on migration and data loading into Redshift. And then on Thursday, at the same time, 9 a.m. Pacific, we'll be doing a session that focuses on reporting and advanced analytics with the focus on some actual customers talking about their usage of Redshift. At this point, I'd like to turn it over to our presenter, Sanjay, to begin today's session.
Thanks, Greg. Appreciate the introduction. Hello, everyone, and thanks for joining the webinar. Appreciate you taking the time to join us today. We've got a packed agenda where we're going to cover topics from distribution, sort keys, compression, and some additional topics that will help you optimize your Redshift cluster. I work with a lot of customers who use Redshift, and some of the key points that I'm going to address today come up as things that they need to implement in order to optimize the performance on their cluster. So let's get started. So Greg mentioned that this is a webinar for users who already have some experience on Redshift, but just to recap, let's take a quick look at the Redshift architecture. Redshift architecture consists of a leader node and underlying compute nodes. The leader node is actually the SQL endpoint. It stores metadata that contains information about the compute nodes, and it actually pushes down the query execution to all the compute nodes where all the data is stored, and then the query is processed in parallel across all those nodes. Data is loaded in parallel into these nodes via the AWS Simple Storage Service, or from our DynamoDB NoSQL service, or through an SSH tunnel. In addition to that, just to recap, there are various types of nodes available to you. There's the DS2 type node, which is HDD based, anywhere from 2 terabytes to 2 petabyte clusters can be created, and the DC1, which is SSD based, anywhere from 160 gig to 356 terabyte clusters can be created. One important point to note about Redshift and the nodes is that each node consists of slices, and each slice has its own share of CPU, RAM, and disk. So below you can see that the DS2 node type has 2 slices on the XL node type and 16 on the 8XL, and the DC1 has 2 slices on the XL and 32 on the 8XL. These slices really relate to a lot of the topics that we're going to talk about today. And the first one is distribution. So Redshift has something called distribution styles when you are designing your tables. And it's very important in Redshift that you consider your table design, because a majority of the tuning in Redshift is going to be at the table design level. If your tables are tuned correctly, there's not a lot of tuning that you'd have to do on the query side unless the query is just written badly. So tuning at the table level is going to be very important. Let's look at the 3 styles that you have the option of choosing. There's distribution key. Here's where we want to put the same keys in the same location, and we'll step through an example. There's distribution type of all, where all the data is on every node. So that same table is copied to every node in the cluster. And distribution even, which is the default distribution. And this is where in a round-robin fashion, data is spread across all the nodes. So one of the examples I want to use is an example here where I've got a CloudFront table, I've got a user profile table, and let's see how co-locating the data is going to help us improve our join performance. So when you use distribution key, in this case our key is user ID, records with the same distribution key for a table are going to be on the same slice. So if I wanted to do a join with the user profile table, you can see that the user ID 1234 is also on the same table. So that is actually, that locality is going to help me with my join evaluation. I've put together an example for all of you to look at, and this one is based on the TPC-H dataset. This is the Transaction Processing Performance Council dataset. This dataset is available to you to download and test out yourself. What I did here is I created two different sets of tables. So I have an orders table, I have a line item table, and I created those two tables with the distribution key of order key. And then I created another set of the orders and line item table, but I didn't define a distribution key. I left them as distribution even. And when I ran my query, when I defined a distribution key, the performance is significantly faster than when I didn't define a distribution key. So as you can see, in this case, 178% faster, pretty significant. I do want to state that different workloads are going to have different performance results. I'm running a sample data set here on a 2-node 8XL cluster with a significant amount of slices. But if I was running one node, these numbers would look a little different. However, the distribution key would still give me a performance boost. So let's take a look at some tools you can use to figure out why, why is the distribution key faster? Redshift, like many data stores out there, gives you the ability to take a look at the query plan. So in this case, we'll compare two query plans. So at the top, you'll see the query plan for tables with the distribution key. And at the bottom, you'll see the query plan for when I ran the select for tables without a distribution key. At the top, and highlighted in blue, you'll see a ds underscore dist none. And at the bottom, you see in red ds bcast inner. What happened when we didn't have a distribution key is that the data that needed to be co-located on the same node was not, and cross-node communication needed to happen in order to join this data together and present the results back to you. And that's why, without a distribution key, this took a lot longer to process. So a couple of ways to access the query plan. One way to do it, you can do it in the console after your query has already been executed. And you can also get the actual query plan, but you can also have a graphical representation of that query plan. The other way is, before you actually run the query in your SQL tool, you can actually run the select statement without actually running it for results, but you can put the explain clause in front of it, run the select, and it will actually generate the explain plan. So on the screen prior to this one, that's how I generated my explain plan from a SQL tool that I use. And what that did is help me figure out that it seems I have some kind of problem with cross-node joins, and that's because of my distribution key was set at even. The query plan, we have a lot of detailed documentation. You can see the link on the slide that will help you understand how to interpret the query plan and use it accordingly for your Redshift cluster. One of the things I want to introduce all of you to is a set of tools that I use. A lot of our solutions architects and our database engineers also use. Initially, these tools were put together by Eric Ferreira, who will be answering your questions today, our principal database engineer from our Redshift team. And we've had some other contributors as well to these scripts. But these scripts are really key in determining if your cluster has been set up in an optimal way, whether it's tables or sort keys. I use them with customers all the time. Anytime a customer will want to do a review of their cluster or talk about a performance problem, I'll want to run these scripts with them and take a look and see how have they set up their tables, are their sort keys defined, is their compression being used. So along with the set of scripts, there are also AdminViews. You can create these views in advance. Anytime you need to take a look at them, you can just run a query and get the results. And we'll take a look at an example. So one of the things that can happen if you don't use a the right distribution key. A poor key choice can lead to uneven distribution of records, and if that happens, that will actually cause processing imbalances, because you may have some nodes that will return the results faster, although you won't see them on in your SQL window, and some nodes that are taking longer to complete the SQL query just because they have more rows or more data on the specific node. So the idea behind distribution keys also to make sure that all the nodes across your cluster has a balanced number of records, so, as represented in this graphic. So you can see that I ran a select star against the check data distribution view. And when I do this, it's going to give me a return result and tell me that whether my data is balanced across all the slices in my Redshift cluster. So what are the guidelines on what type of distribution you're going to pick? So distribution even works great when there are tables that are not going to be involved in joins. They're not going to be involved in any group bys. And they could be small dimension tables where rows are under 1,000. Distribution key, you want to use that for large fact tables, large dimension tables. So in the example that I used, my line item table has 6.1 billion rows in it. And so distribution key really helped me get a better result for my query. And distribution all, this is the distribution style where a copy of the table is kept on each node. You want to use this for medium dimension tables, so 1,000 rows to about 2 million rows. And these are rules of thumb. You can implement these and run some tests and see how they're working out for you. One of the scripts that I want to highlight, and you'll actually see the script come up quite a bit in this webinar, is the table_info.sql. And this is a very rich script that gives me a lot of detail. But in this scenario, I've highlighted where it's telling me that I have an extremely large table, the line item table here, time and node distribution table that is 292 gig in size, and it has a distribution style of even. So if I'm designing my my data model or designing my tables, and I see some table this large that has a distribution of even, I may want to go back and check and see, is this the right distribution style? Most likely that table is going to be involved in a join, especially because it's got a sort key. So if it's going to be involved in a join, then I want to have distribution key to improve my performance. One of the other aspects of Redshift that is important to note is the use of sort keys. Sort keys actually help keep data in order in tables, and this actually increases performance because the data is in order. And let's take a look at why. Redshift has a concept called zone maps, and zone maps you can think of it as metadata that holds the minimum and maximum value of each block. So when a query is executed, the zone map is going to be consulted to figure out what values are contained in the zone map, and can entire blocks actually be skipped. So in an unsorted table where there is no zone map, if I run the query that you see on the right side, the select account logs with a date of June 9th, 2015, if I have an unsorted table, the zone map is not updated, it doesn't exist, so I'm going to have to scan through a lot of blocks that I don't need to read. Whereas if I have a table that is sorted and the zone maps are updated, then it's going to ignore all the other blocks and only go after the block that I absolutely need. So in this case, it's going to go after the block that actually has June 9th, 2015. How do you choose sort keys? There are a couple of schools of thought here. So if you have a timestamp column, like we did in the previous example, that is a good candidate for a sort key. If you're doing frequent range filtering or equality filtering on a specific column, that's a good candidate. Join columns. So you might have opportunities to make the distribution key and the sort key both could be the same, and that will give you a benefit in your join queries. So 3 different types of sort keys, and I'm going to walk through an example of each. Single column, compound, and interleaved, which is something we introduced earlier this year and has a significant performance benefit when you're actually querying for data that has the queries filters are going to change between different user to user. So if I defined a sort key, a single column sort key, this is most likely going to be on some kind of date column because date is my primary filter in my query. And what this will allow me to do is speed up my joins and my group bys. But one of the things it will also help me do is if I do my vacuum operations on this kind of table, they're going to be significantly faster. For those not familiar with vacuum operations, that is a maintenance operations that does 2 things. It reclaims blocks that had previously had data and that data was deleted, and it also resorts all the data in a table to put it back in sort order to improve your performance. The compound sort key, in this case, I have date, region, and country in a compound sort key. This is where I might have a query where I want to use the first column as my primary filter, and then I want to filter on the remaining columns. Again, this can help me with joins and group bys, but it's going to be a little bit slower to vacuum because now I have 3 columns in my sort key and all 3 need to be sorted. The interleave sort key, when I create this, it's going to give equal weight to each column. So if I have users that want to use queries on a particular table and change the filters on a frequent basis, I can define up to 8 columns in my interleave sort key. But note that this is going to be the slowest to vacuum because I'm going to have up to 8 different columns that I need to sort. So that's going to be a bit slower. So we'll talk a little bit about that as we go on as one of the considerations when using interleave sort keys. So here's an example. This example can also be found in our documentation. And in this example, I've got 3 tables. One that defines a single sort key. The second table defines a compound sort key. And the third table, which defines an interleave sort key. So this is actually the syntax that you would use when creating these sort keys. And in the next example, I'm going to run queries against all 3 different table types. So query 1 ran it 3 times against each table type. So against the single, the compound, the interleaved. Query 2, I'm going to run it against all 3 tables again. But in this situation, the second column and the third column are in my filter in query 2. And in query 3, I'm going to run it against all 3 tables. But in this case, column 3 is my first filter and column 2 is my second filter. So let's take a look at how that performed. We'll focus on that last row, the interleaved row. And you can see that for query 1, where I had a single key, it actually took longer with interleave sorts to complete my query. But it's query 2 and query 3 where interleave sorts gives me the biggest bang for the buck in terms of performance. So you can compare 1.6 seconds versus 18 plus seconds, or 0.8 of a second versus 30 seconds. And what happened here is that equal weight was given to the columns that I specified in my query. But even though I specified the third column before the second in my filter, I still got a performance benefit. One of the things you want to consider when you use interleave sort keys is that you will have increased data load times, because when you're loading the data, it's going to need to be sorted across up to 8 different columns. And when you vacuum, as I said previously, when you vacuum an interleaved sort key table, that's going to take longer just because of the amount of columns that are in the sort key itself. It is also more effective with larger tables. So rule of thumb is 100 million rows plus. You may want to consider interleave sort keys for those type of tables. And the other thing you might want to do is that if you have a table that where you're appending the data in sort order, and that could be something where you're putting in logs into a table, and those logs come in an order of some kind of timestamp, then you may want to use a compound sort key instead of interleaved, because interleaved is not going to ingest that data in sort order, although the compound sort key is going to ingest the data in sort order. So a few considerations to think about when you actually use interleaved sort keys. Going to go back to my table _ info SQL script here that you can download from GitHub, as I showed previously. And here you can see that I can run this and get a listing of all my tables and be able to view and say, are there any sort keys that are missing? Should there be a sort key on this table? So when you're working with your team and designing the tables, or you might already have something in dev and test, and notice that a specific query maybe is not performing up to par, then it's possible that you need a sort key, whether it's single, compound, or interleaved, based on the guidelines that are provided. A lot of the details that I've provided are also in the documentation, but I wanted to show you some clear examples of how they work. One of the other benefits of Redshift is compression. And Redshift has a number of compression encodings available to you. There are two benefits of compression. One is that you will actually compress the data, and you can get a compression ratio of anywhere from 2 to 4x, depending on the type of data. The other benefit is there's a performance benefit, because you're actually going to be pulling less data from disk, which actually results in better I/O performance. Compression, when you actually first create a table with your DDL and you first load the data using the copy command, Redshift is actually going to load a certain sample rows into the table, determine the compression algorithms, and then recreate that table with the optimal encoding. However, that may be okay if that table is not changing a lot and you can opt for Redshift's automatic compression. But if you're using temp tables to load data, or staging tables, or time series tables where the data loading is very, very frequent, you can actually reduce some time off of the copy command by adding the comp update off flag. Now, in this case, compression will not be done automatically. What you will do is actually run your DDL, run the analyze compression command against that table, and Redshift will make a recommendation on the right encodings for that table. Add those encodings to your DDL, recreate the table, and also add it to your processing. So if you're creating those tables on the fly, add that DDL to those scripts, and now those encodings are already there when the data is being ingested, and you can shave off a certain amount of time and avoid that automatic compression, but still have compressed tables that give you the performance benefit. So here's an example. On the left side, you'll see compression encodings where I have tables, two tables that are compressed. And on the right side, you'll see that I've skipped the compression encodings. And if I run the same query that I highlighted earlier from the TPCH dataset, you can see that the compressed table performed significantly faster than the uncompressed table. And again, this is because less data stored on disk, less I/O in getting that data back out when I execute my SQL query. So one of the things to look out for as a rule of thumb is that you may want to skip compressing your sort keys. And this is because when you compress your sort keys, it's possible that your data columns are significantly larger than, or if your sort keys compress significantly larger than your other columns, then you may want to skip compression as a rule of thumb, I recommend that you skip compression on the sort key anyway, because highly compressed sort keys means you can have a lot more rows per block, and all of those will need to get read. And so you'll actually be scanning more blocks than you need. So as a rule of thumb, you actually may want to avoid this. The table info SQL is something I use as a versatile tool to be able to even take a look at how many tables in my database, in my Redshift cluster, are compressed. So if you look at, there's a column here at the end of the red highlighted box where it says ENC for encodings, and it actually says N for no, which means this is not a compressed table. And if I look at the size of this table, it's significantly larger. This table is 840 gigabytes plus compared to the 294 gigabytes for my compressed table. So you're saving space, but you're also getting a significant performance benefit. So I want to address DDL, and there's a couple of tips here to provide you when you're actually designing the tables in terms of your column lengths. So let's take a close look at this table, and you can see that I'm very particular about the length of the columns. So my varchar is at 79, my char column's at 15, my order status is at 1. And the reason I've done this is because with Redshift, you want to keep your columns as narrow as possible. If you have a column that requires varchar 20, don't make it 20,000. And the reason why you need to do this is because if your columns are wider than needed, then actual memory is being wasted. So when you're running complex queries, a lot of the results, intermediate results, can be written to temp tables. They can be written to temporary disk space. These temp tables are not compressed. So what will happen is additional memory is going to get used behind the scenes, which will actually affect the performance. So be mindful of how wide your columns are going to be, and only really allocate what's required. The other thing to note about DDL with Redshift is you can define primary keys and you can define foreign keys, because they'll actually help you. They'll actually help the optimizer with the query plan. However, note that they are not enforced. But one of the things that you'll learn in the data loading webinar tomorrow is that with Redshift, you can use a manifest file. So if there's any concern that a specific file is going to be loaded twice, if you use a manifest file with Redshift, then only the files that are in the manifest file are going to get loaded. So those details are going to be highlighted in tomorrow's webinar. And since it's more on the data loading side, it's not included here. But the primary and foreign keys, defining them in your tables is going to help. One of the places I've seen this happen is when people create copies of a table where there's foreign keys and primary keys, and then the copy doesn't perform well because the keys weren't inherited. And I'll cover that a little bit later in this webinar. So data loading, a couple of slides I want to share, a couple of tips I want to share with you on data loading. There'll be more insight onto this in tomorrow's webinar. But if you have for example, 16 gigabyte file, you want to make sure that you actually split that file. So in this example here, if I loaded that file as a single input file, I'm not taking advantage of the parallelism that Redshift provides me with all these slices per node. So in this case, with one file, I'm not going to get the performance that I need. So instead of 100 megabytes per second, I'm only going to get about 6.25 megabytes per second. If I take that 16 gigabyte file and I split it into 16 files, then I can actually run all 16 in parallel. Each file will run on a particular slice, and it's going to load much faster. And this can be done if you split your files and they're loaded into S3. Your copy command is still one copy command, and it's going to know that there are multiple files behind the scenes, and it will load those files in parallel and reduce the data loading time. One of the other things I want to highlight is that commit stats SQL, which is another admin script that I think is very, very useful. And this comes in handy to see if your commit queue is backed up. So you'll learn a little bit more about this in the data loading webinar, but with Redshifts, when you're doing inserts through JDBC, ODBC from some external system, those inserts are going to be slow because behind the scenes, each column in Redshift, each column is a single file. So if you can imagine an insert that has multiple columns is going to actually hit a single file. And if you're actually going to have, if you're actually inserting 100,000 rows and you're having some kind of commit statement after each insert, that is actually going to affect your commit queue and actually affect your performance. So if you absolutely have to do insert and can't use the copy command, you actually want to batch your inserts in a multi-line insert, and you want to avoid issuing commits as much as possible and only issue a commit at the end of that specific batch, because the commit queue can actually affect the performance of the queries that are coming in and actually slow down your operations. Earlier I'd mentioned the vacuum command. This is an operations and maintenance feature in Redshift. So vacuum can affect performance if you don't vacuum frequently, and let's highlight that a little bit. So you can actually run it in 4 different modes, and each of these modes has a different way where it can either reclaim space or not, or resort the table or not. One of the common ones is reclaim full, where if you had deleted rows or dropped any tables, the space is going to get reclaimed. But where you have sort keys defined, it's actually also going to resort all the rows if you had loaded data out of sort order. There's vacuum delete only, which can reclaim space, but it does not resort any of the data. Or you can vacuum with sort only, and it could be where maybe I didn't delete a lot of rows, but maybe I loaded everything out of order, and I want it back in some kind of sort order so I can have efficient queries. And finally, I can use vacuum reindex, and that's going to be used when you have interleaved sort keys defined. One thing to note, though, that vacuum is an intensive operation. So if you don't vacuum frequently, it can actually take even longer to vacuum your Redshift cluster. So to minimize the impact of vacuum, the recommendation is that you vacuum on a regular schedule. So define a maintenance window in your Redshift cluster, depending on what your business requires. Could be something on Saturday night, could be early Sunday morning when you don't have your business users logged in, and you can actually run your vacuum operations at that time. There's some other options here that you can see on my screen, and the other one I want to highlight is that if you have a significantly large table, rather than vacuum, you may want to perform a deep copy because it's actually going to be faster. So let's highlight what the options for a deep copy as an alternative. So what you can actually do here is that rather than running a vacuum command, create a copy of the table using the options that we have here. I'm going to talk about the best option, and then you can always rename the new table and then drop the old table. So the best deep copy option that you should use is actually take your original DDL, create the table, and then run a insert into select from statement, and that is actually going to not only be faster, but it's actually going to retain all the table attributes. So the other options like create table as, while you can create a table doing it that way, you won't inherit the primary key or you won't inherit the foreign key. So I've seen users where they may create a copy of that table by using create table as in a different schema and not get the same performance as the table that has the primary and foreign keys, but that's because these don't get inherited. So the best option here is to actually do a deep copy using my original DDL, and then doing an insert into select. So a lot of us are who work with database engines are familiar with keeping statistics up to date in a database engine. And one of the key features of Redshift is the analyze command. So Redshift's query optimizer also relies on statistics. So you want to keep the statistics up to date as much as possible. One of the things you can do is that if you're loading data frequently on a daily basis, at the very least, you want to make sure that you update the statistics on the sort and the distribution columns after every load. And then once a week, you want to actually analyze all the tables in the cluster that have newly loaded data. And this is actually going to help your performance rather than hinder it. So this is something that you should also build into your maintenance window. This can be done pretty much around the same time. The full analyze can be done around the same time after vacuum has been completed. The stats on the distribution columns and the sort keys can actually be done after every data load. And you can actually take a script from the AdminScripts. Here I have one called missing table stats, where you can run these as part of your monitoring. So even though Redshift gives you a lot of monitoring aspects within the console in terms of CPU, network I/O, write IOPS, and read IOPS, these scripts that I'm talking about give you some additional insight, and you can actually run these on a weekly basis just to make sure that you don't have any tables that needed to be analyzed and have actually been missed in the process. This script will actually help you collect that information. So workload management is actually a mechanism that we provide you so that you can actually create different workloads, different queues for different workloads in your cluster. So say, for example, within the data warehousing world, we're always familiar with long-running queries and short-running queries. And sometimes the long-running queries will take up all the queues where they take so long to run that the queries that are shorter are left waiting for a queue and may take longer to process just because they don't have the access to get on a queue and finish. So in this case, workload management is a tool that we provide you to be actually able to split up these into different queues and run them separately. So an example I have here is I've taken my Q1 where I have 10 concurrent queries that can run for my business analyst, and these are small queries. However, I might have large queries, I might have huge copy commands and ETL that needs to run off hours or on weekends, and I want the bulk of the memory to be allocated to those queues. So in this case, I've allocated 65% of my memory to large queries and ETL processes and copy commands, and I've left a smaller amount of memory for my faster queries. The other thing I want to point out about workload management is try not to set more concurrency than you need. So in this case, this example, I've got 15, I've got one queue and I've got 15 concurrent users that can run queries here. And these could be small queries, some large queries, but I know that in the evening I want to do my batch processing. I want to run very large queries. So I want to make sure that other business users aren't going to take up these queues with some kind of runaway query or take up queues that I need at night or take up the memory that I need at night. So I can actually go into my SQL tool, log in as the user that does all the batch operations, and I can actually set the next set of reports or queries or copy commands that are going to run on a particular query group. So in this case, the select statement that you see here is going to have the full share of the memory on the cluster, and other query users are not going to hinder those operations. So try to only use the amount of query queues concurrent queries that you need, rather than saying I need 50 in one queue when you really only need 5. So my email is on the screen. If there are any questions, any scripts that you need that I may have talked about, or any commands that you want to learn about, feel free to send me an email. I've also highlighted the best practices pages in our documentation that you can refer to, where a lot of these best practices are referred to in even greater detail. And then I'd also like to encourage you to join the webinars tomorrow and on Thursday, where tomorrow you'll learn about migration and loading data into Redshift, and on Thursday learn about reporting and advanced analytics in Redshift.
Great. Thanks, Sanjay. We just wanted to recap and remind everyone that a recording will be a link to this recording, as well as an email will be sent to you shortly with the information how to retrieve once we've been able to do a sound check of the webinar. So you'll be able to get access to that, as well as we'll be doing a quick survey to understand your satisfaction with the content and the presenters from today's webinar. So as you know, with Amazon Web Services, we're very interested in getting your feedback, and that helps us define future topics, as well as being able to provide to you the best information possible. So your feedback is definitely well appreciated. We will be starting in a few minutes here our questions and answers. I know that Eric has been busy in the background answering questions. So once we get the survey complete, we will go through the Q&A session that Eric will lead via audio. To submit your questions, again, please just use the chat window, and Eric will address them shortly once we finish the survey. Okay, we're just getting a few last survey results in, and then once the survey is done, Eric, you can pick it up and pick up the Q&A. Thanks. Yes, they're going to say you're.
Okay, thanks everyone. This is Sanjay again. I'm going to start answering some of the questions. Got a question here. When using copy to load by SSH, are multiple files loaded in parallel when loading from S3? Yes, so when you're doing it from SSH, multiple files can be loaded as well. I'm going to go through some more questions here. So I've got a question here. Can you talk about the parameters for choosing the size, the number of nodes in the cluster? That's a good question. So the number of nodes in a cluster is actually going to depend on the growth that you're going to experience. So if you're growing by 1 to 2 terabytes per month, then you may want to use the 8XL types because they have more storage on them. If you're not going to grow significantly large, then you may want to use the smaller nodes. And then you may want to consider the performance. So HDD versus SSD. Of course, the HDD disks perform well, but we all know that SSD performs much faster. So that's an option as well. So Eric is also going to pick up some questions here. So just going to introduce Eric Ferreira, who's our principal database engineer on the Redshift team.
Hi, I see a question on translating SQL 2000 text column to Redshift. The varchar max on Redshift will be 65,000 large character, and unless you really have that amount and you really need that amount to be there, you will have way more space used during the query processing that you need. So if varchar 255 or 260 as your example here is good enough, you should keep it as small as possible for the data that you really need and the data you really need to do analytics on. Don't consider Redshift as like a backup system for saving whole pages and on that stuff. Normally, those very large objects you could save into an S3 bucket and then have on Redshift table just the link to that big object if you're not going to do specific analytics on it. There's a question about recommendation on importing varchar columns. On Redshift, all the character types are able to receive UTF-8 characters. The only thing that you need to be aware of is that SQL Server, for example, when you define the size of a column in varchar, you define the size in characters. So 20 character in varchar string can have 20 characters, but those 20 characters can be all 4 byte UTF-8, so then you have 80 bytes. On Redshift, when you define a column size, you define in bytes. So if you have an in varchar, your safest option is to make it times 4. Of course, if you know your data well enough to see how much of your data really has 1, 2 byte characters or all the way to 4 byte characters, then you can analyze your data and maybe not go that far on 4 times, but the safest will be 4 times wider, because on Redshift the declaration of varchars and chars are in bytes, not in characters, and your n varchar can expand, 1 character can expand up to 4 bytes on it. I've seen a few questions on UDF availability timeline. I know we announced that feature last November, and then we've been busy making it ready for customers. So all I can tell you is it'll be soon. But since we announced, we really are very close to getting it done. I have a question on concurrency about where you can truly process simultaneously. When you have your workload management setting to 15 or to 50, which is our maximum for total concurrency, the memory is divided by the number of slots you create. So if you say I can have 5 queries running at the same time, we divide the total memory available per slice into 5, and each of those one using will have ownership of that memory. And then if you do 50, then you divide the memory by 50. That's why it's important to define your concurrency workload management as as much as you need, not a bunch more, because then you are just giving yourself less memory if you're going to have a lot of empty slots. So you could, at issuing your queries, you can say on the session side, they say, I want this query to use 2 slots or 5 slots, so you can use extra memory for each session. It can give you some dynamic allocation in a sense. So there's a session variable that you can set up that says WLM query slot count, and if you set that before issuing the query, on that session, that query will try to use the number of slots you chose. Default is 1. And of course, if you don't have, like you say I want to use 5 slots, and if you don't have 5 slots available, your query hangs on queue until 5 slots become available, then you can run the query, right? And the queries actually are treated run simultaneously. There are slice level workers that do the job for each of the queries that I've been executing. And there are other resources on the cluster, like I/O and network, that are also shared by all the slices or are shared between all the queries on a given slice. So the work, it's like a queue of different steps of work that is given and distributed, for the main processing of the query and the reporting back to the leader node for the next step and so forth happen truly in parallel. And the only resource that we parcel out to customers is RAM. Everything else, it's a shared resource that gets shared dynamically as much as needed during the query execution. There's a question, there's a concept like buffer cache for storing blocks in memory? Yes, Redshift has a cache, so every block that you read from disk to be used gets saved into a cache, and before I read a block, I check if the cache has that block for me. Usually the first couple blocks on every column of every table always remains in memory so for quick access, and then after that, this remaining space gets allocated and deallocated by a last used algorithm. Somebody's asking about automatic compression. I saw other questions about automatic compression, right? The automatic compression is very useful for a one-time load of data, and Redshift compression is not only for saving space, it will save performance because I have less blocks to write and less blocks to read. And if I'm running a table one-off, I can safely use the automatic compression. The system will compress the data and as much as it sees the first amount of data. If you're talking about either a very large table that you're going to keep for a long time, or a staging table where I copy every day to a brand new table, but the data itself is known to me, then it's better to not use automatic compression, to load some significant amount of data, do analyze compression on the data after loading, and then recreate those staging table or recreating your main table with that compression. And then you don't use automatic compression, because if every day you load the same type of data into a brand new table, you don't want to do automatic compression. The automatic compression, what it's going to do is going to load a few thousand rows per slice. It's going to try to compress every column of every possible way, and then return the one that return the least amount of blocks. And then I drop the table and start loading all over again. So that overhead you want to do once, right? Not every day or every load or every hour. So you want to be very careful about automatic compression, like the presentation said about it. Somebody's asking about joins making performance slow. Joins will make performance slow with a few situations where the data has to be distributed. So then having the proper distribution key or getting your dimension table to be just by wall can help with that. If you're joining two very large tables, and there's not a lot of filter, you're doing a very large, the two tables we're searching are large, and the intermediate results is also large, building the hash table can be a performance problem. On that case, there's a few choices around there. One of them is if you give more slots, you give more memory, so the hash table can have more memory to run. That might be one thing to do. The other thing, if you have two very large tables that you join all the time, and it is possible to make both tables to have the same distribution key and the same sort key, and both are the same and are the column you're joining on, and you keep those two tables vacuumed all times, right? Then you can do a merge join, which on this very particular case, which is not very practical for generic use, but on this very particular case can be much, much faster. So the way a regular join works on Redshift, we walk through the smallest perceived table, and the optimizer needs to have fresh stats so we know which of the two tables will return least amount of rows, builds a hash table, and then walks the other table with that hash table in mind to execute the join. So give it more memory will help. Filtering as soon as possible, so if you can filter each table by itself before the join and then join on your SQL, the sooner you put your filters there, the better. And then the third option will be to really have the merge join. Now, the other option on Redshift, since it's a columnar system and it's something you have to test, is that if those two tables are joined too much together and the performance is critical for you, you're looking for seconds or sub-second response time, denormalizing selectively on this case might be an option, and you can do experiments and see if a denormalized version, depending if you don't change too much in the dimension table or you don't have to change things in the back, you can have it perform better on that situation. But then, of course, there are other prices to pay. So denormalizing is always a compromise. You're losing something else, some flexibility or some other load performance. So you have to really test both options. And every time you test something on any BI system, you really have to consider the whole package, like the time to load, maintain, and query my data. Not only, oh, the queries here are faster, but my maintenance might be slower. So you have to kind of understand. You also understand your ratio of read and writes on your cluster to see what it's worth it. Another thing to consider is on join performance is that if the performance of the join is as fast as it can be in terms of being with proper distribution key and its co-located join, also have good stuff. If you add more nodes to your cluster, you divide the data into smaller pieces, so then there are more people doing the work. So it's kind of throw hardware at it. It's another option to speed up. And normally you get, in a tuned environment, you get linear scaling as you add more hardware to your cluster. And that's part of the key on the Redshift part. The massively parallel brute force parallel can do things really fast because every slice is doing a little bit of the work. But of course, the join itself has to be co-located join. Otherwise, you're just sending more data across the network. It's just not going to get any better. Somebody's asking about what's performance using views. Views on Redshift are a compiled code that can be very efficient in terms of you saving your code, and it helps on two things. First, on Redshift, every query is compiled to C code and pushed out to the compute nodes. So when you write a view and everybody uses the view, you kind of increase the chance of that query to be already pre-compiled, so you don't have to pay the price for the first compilation. Redshift does not materialize the views, but having the views encapsulate some of your business logics of some of your things is actually a good idea, and Redshift can execute, and it becomes easy for you to tune your system as you fix a couple views and recreate some views for particular performance characteristics, and then everybody that just uses the view can take advantage of that. You don't have to change codes on your software or anything like that. So yes, it's recommended. Performance views are very well performing on Redshift, and you can even, when you do create or replace on a view, you can replace a view without worrying about underneath objects. So you can have a view of a view, and then the middle view you do a create as replace if you need to change something that doesn't change the signature of the view. You have that flexibility as well. So yes, it is recommended to use views to encapsulate some of your code to a degree. Understand though that on Redshift, some very, very complex queries The optimizer might decide to create temporary tables in the mix to solve that very complex query. When that happens, you can notice, because then we look in STL query, the same transaction ID of your query generated 3 or 4 different queries, and there's a create temporary table, and then you see like a table, temporary table called vote TT something. So when that happens, if you're happy with the performance, that's fine, because the optimizer is doing the best it can to resolve a complex query into smaller steps. Now, that all depends on how good the stats are in your system and how well the query is written. But when that happens, sometimes you want to take a step back and look like, okay, maybe I should myself pre-create some temporary tables that resolve the same kind of data problem, and then I can choose distribution keys and sort keys and keep that table, and then just use it. Because if you use the query over and over again, you don't want it to every time create a temporary table, and if your data only changes once a day, for example, right, you can just have that one step pre-create, and everybody that uses that already can access the temporary table. It's a nuance of very complex query on Redshift. Usually, it performs well, performs fine, but if you're not happy, or you're seeing a lot of distribution of data on a very complex queries, then it's the time to analyze what Redshift is doing and see if you can break in those steps and have temporary tables yourself if that query gets used over and over again, because then you save the multiple writes if your data don't change every 15 minutes. Somebody's asking about update and delete statements. So the question is, when you're issuing update statements, does it delete and insert or update on the basis of PK? Also, any best approach is updates.
Eric, this will be our last question.
Update is a delete and insert. So that's the first thing that you should know, that when you have a table with many columns, if you delete one of them, you actually deleting the whole row, insert a brand new row at the end of the table. Blocks on Redshift are immutable, so actually when you delete something from a table, just mark that row for deletion on the next vacuum. So you don't release the data space, and you just add a new row to the end, and that deleted row gets filtered out when you query, so you don't see deleted data. So updates on Redshift should be cautiously used, right? If you have a small staging table or temporary table that you're doing some updates as part of the ETL, the update itself will perform fine, because you're going to just mark a few rows as deleted, insert brand new rows, and then at the end of the day, you do insert or select from the staging table to the final table, and the final table only has an append, right? What you don't want to do, or you want to try to avoid, is you have very large tables, and on those large tables, you do updates sprinkle across the data across multiple days, right? That can become expensive, not for the update itself, but for the maintenance of the table, because next time you run vacuum, start on the first block that shows up a deleted row, I have to start rewriting the table during vacuum. So that can be very expensive. So on a BI operation in general, you really want to try to do as much as pending as possible. And if you're talking about dimensions, type 2 dimensions work really well on Redshift for you to get the latest version of the row. So those are the strategies to try to avoid updates. Of course, if you really cannot avoid updates, you just have to know there's a price to pay, and your vacuum will be expensive, or maybe every week you're going to have to do a deep copy of the table to get it back in shape. And up to a certain amount of percent of updated rows, you won't affect your query performance until the Redshift scans too many deleted rows to return real rows, and then there's an alert shown on your queries that if you can query for it, and you can see, well, this particular table, the alert is complaining about scanning too many deleted rows, it's time to run a vacuum, or it's time to run a deep copy on that table. I hope that helps answer the question about updates on the table.
Great. Thanks, Eric. Unfortunately, we're out of time for today's webinar. I'll just remind everyone, in case your question did not get answered, we do have the Redshift forums where you can post questions into the forums. As well, as a quick recap, today's session was best practices for optimizing Redshift performance. Tomorrow at the same time, 9 a.m. Pacific, we will host a best practices webinar on data loading with Redshift. And then Thursday at 9 a.m. Pacific, we will host reporting and analytics where our partner from Looker as well as a customer from Yahoo will be presenting their actual usage of their Redshift systems. So again, thanks for everyone's participation today. You will receive an email with today's recording, and we look forward to hearing from you soon. Thanks, everyone.